All right, let's look at an example here of how I could actually go ahead and use this concept of a line integral to actually compute something. Take a look here at example 1. Suppose a wire can be modeled by the upper half of a unit circle, which is given by x squared plus y squared equals 1. No surprise. If the linear density of this wire is measured by this function for any point on the wire, then set up and evaluate an integral which represents the mass of this wire. Okay, well, based on what we already talked about, we know this. We know that the mass is automatically going to be equal to, I'm going to integrate my density with respect to S, with respect to arc length, as I move across the curve C. And here again, C is the upper half of the unit circle. Okay, so in order to go ahead and attempt to simplify this though and compute it, I'm going to have to make use of what we talked about in the last video. While this is a perfectly reasonable setup, the calculation is not easy in this form. So what I'm going to have to do is find a parameterization for C. So I'm going to go ahead quickly here and just draw out where my C actually is. So here's my unit circle. And C is just this top portion, right? So this is my C up here. There's my C. And I want to find a parameterization for it. So I'll start by saying we must parameterize C. So maybe we can say that R of t could be equal to, what's something I could use to graph a circle? Oh, we've actually talked about this a lot in this course. You might remember it involves some trig functions. Yeah, some stuff that I might be able to use here is like a cosine of t, comma, a sine of t. And I don't need any coefficients on those sines and cosines because remember the coefficient determines the radius of the corresponding circle, and I want radius 1. Of course, though, I'd have to specify exactly where t is. So what are the different angle values that I'm going to use? Well, I could also go here and use something then like 0 to pi. That seems perfectly reasonable. So while this is a parameterization, it might not be the only parameterization. It's definitely a good one though, and we can attempt to use it. So let's see what begins to happen when we start to make this replacement now into our mass formula. All right, so let's see. Oops. So our mass calculation now should be able to be converted into an integral that goes from 0 to pi. We're going to have to change out our function though. Our function used to be 2 plus x squared, but now I have to say, what's x? But I can see here that I have a formula for x and even a formula for y. So I'm going to use those. So I'm going to have cosine squared of t times the sine of t. So I still have x squared times y. And then I can go ahead and state that when I replace my ds, I'm going to have to replace that again with, remember what we stated up above. I'm going to have to replace it with an r prime of t and its magnitude, and then dt. So I'm going to do that here. Remember that that's going to ultimately look like the square root, and then I'm going to have derivative of the x, which should be negative sine of t, and that's going to be squared, plus the derivative of the sine of t is cosine of t and squared. Finally, dt. If I can evaluate this, everything's good to go. Now, fortunately, this is actually really easy to do. Take a look at that radical over there and see if you can simplify it all the way down. Yeah, I mean, if you look at it, you might pop out to you right away that that over there is really just going to turn into just a 1. So I'm just going to end up with a dt. So now I can go ahead and attempt to compute this fairly quickly. Let's see what we come up with. I can see here that I'm going to get a 2t, and then, the integral of this part here isn't too bad. You might notice that you can kind of think about doing a quick u substitution on that second part, where like if u is a cosine, then du is a negative sine of t, and dt. And so you might be able to come up with the following. This maybe looks like it's a negative 1/3 cosine to the third of t. And I just have to evaluate that from 0 to pi. So let's see, that's going to be 2 pi minus a third cosine cubed of pi, and then 0 minus a third cosine cubed of 0. I think if you simplify this all the way down, you're just going to end up with 2 pi plus a third, ultimately minus a negative a third, and so I get 2 pi plus 2/3. So I believe that the mass of the wire is exactly 2 pi plus 2/3. That's the mass. Okay, so this kind of demonstrates how I can actually go ahead and use what we had talked about to evaluate one of these line integrals. If I don't understand how to convert out of this form where I have my function ds and the c, I'm going to always be completely stuck. As you'll see here in the notes, one of the biggest challenges for calculating line integrals is finding a parameterization. Okay? And of course, I can remember that if I looked at that alternative expression, I can also imagine that this number here can be thought of as the area of a sheet formed between the curve and the actual function. All right, in the next video, we'll take a look at some more definitions and some more examples.